Welcome back to Chemistry with Mr. Kubuske. I am Mr. Kubuske. If I sound a little tired, it's because this is actually the third time I've done these notes today. But we don't need to get into all that. Hopefully this one works this time. But we're still in Unit 3, which is all about atoms. Today we're going to focus on the nucleus of the atom and something that's called nuclear chemistry. We'll talk about radiation and the different particles that are lost during that radioactive decay. But you're supposed to use these answers and these notes as a guide to help you finish your Chapter 25 discovery questions. Rather than taking formal notes, I had you do discovery questions from Chapter 25 that you were supposed to answer. I'll help you answer those questions through these notes, this video, but you were supposed to do this on your own. This is supposed to be a guide to help you understand why those answers are the way that they are. Okay? So I'm going to go a little quick because, like I said, this is the third time doing it. But radioactivity is a spontaneous emission of particles. There's no starting or stopping it. It just happens. Okay. Examples of radioactive elements, the popular ones that you'd hear about all the time, uranium, plutonium. But even our simple ones like oxygen and carbon can even be radioactive. The energy emitted is known as nuclear radiation, and it can produce heat. Remember, heat is a form of energy, so nuclear radiation can feel like heat. Why are atoms radioactive? Well, it's because their nuclei are too big, they're unstable. For example, carbon-12 is our common isotope for carbon. Carbon-14 is a radioactive isotope of carbon. So its nucleus is way too big. So it'll start to vibrate because it's unstable, and it'll start to shoot off little particles, shoot off a little particle until it becomes stable. Well, when it becomes stable, it's actually no longer carbon because it's lost the little particles. And so, therefore, it's become something different. And now, when it's a stable, atom, it's no longer what it was. So, when do they stop becoming radioactive? When they become stable. And the term stable just means constant or unlikely to change. Radioisotopes are just unstable isotopes. And then, what accompanies these changes in an unstable nuclei? Emission of large amounts of energy. Every time we lose some of these particles, we're losing energy as well, and that's what can be dangerous about these radioactive isotopes. Key point here, nuclear reactions are different than chemical reactions. Chemical reactions need something to start them, usually adding heat to them or putting two things together, stuff like that. Nuclear reactions don't need that. They just happen. There's no starting or stopping them. They just go until they become stable. Now, what will cause radioactive decay? That's the releasing of particles and energy by the radioisotopes. That's the pew, pew, pew that I'm talking about. Okay, the process stops when the isotope becomes stable, and the atom is now completely different. It's a different element than it was in the beginning once it has broken down, once it has decayed at the end of a nuclear reaction. There's three types of radiation, alpha, beta, and gamma. The alphas are the biggest, gammas are the smallest. We'll talk about each one of them here shortly. Helium ions are also known as alpha particles. So this is the first type of radiation, alpha radiation. We call them helium ions because they have a mass of 4 and an atomic number of 2. Well, that would tell you that they have 2 protons and 2 neutrons. No electrons in this helium ion. Sometimes alpha particles, well actually most times, you'll see me write alpha particles as an A, but anytime you see that 4/2, that's going to tell you that this is an alpha particle being lost. Let's show an example of nuclear decay. For example, we have uranium here. Uranium has a mass of 238. It has an atomic number of 92. It breaks down, becomes thorium, 234, and 90. Well, what have I lost here? Well, in the top number, 238 minus 234, I've lost 4. And the bottom number, 92 to 90, I lost 2. 4/2, we just said, is an alpha particle. So when uranium decays and becomes thorium, it loses an alpha particle. And this is what that would look like. Here's my uranium. There's my alpha particle. And here's my smaller nucleus now because I've lost a mass of 4. You'll notice the nucleus got smaller. Think of the little checkers here as protons and neutrons. Don't feel like you have to draw all the little circles inside of them. Okay. So what happens to the mass and atomic numbers when we lose an alpha particle? Mass decreases by 4. Atomic number decreases by 2. A balanced nuclear equation should have products and reactants equal on both sides. I may have to add things together on one of the sides to make them equal, but the numbers should be equal on the left side as they are on the right side. And alpha particles, actually, when they hit your skin, will bounce right off your skin because they're so large. Okay, they're strong. They have a very strong charge, a 2+, because they have those 2 protons and no electrons to counteract them, and they have that large mass. So they're really not going to penetrate surfaces. They'll bounce very easily. Beta particles, on the other hand, will penetrate surfaces because they have no mass. Well, they have a teeny tiny little mass because they're basically just an electron. It's a high energy electron from a neutron decay. And you'll notice here I've written an isotopic symbol for a beta particle. It has a mass of 0 because it has no protons and neutrons. It's just an electron. And since it's the opposite of a proton would be a 1 down here because it has 1 proton. Electron's the opposite, so we put -1. The formation of a beta particle comes from the breakdown of a neutron. So I start with a neutron, 1 over 0, and I just write an n for a neutron. Okay, and then I'm going to lose a beta particle, so I'll have a 0, -1 beta. Well, what I'm left with then is a proton. If you think about it, 1 minus 1 would give me 0. 0 minus 1 will give me -1. So that's how that equation works out. So I started with a neutron. It breaks down into a proton and a beta particle. The reason that beta particles have a 0 is because they have no mass. They have no protons and neutrons, and the -1 means that it has a negative charge. It's the opposite of a proton. So let me show you the equation for carbon-14 breaking down into a beta particle. Remember, it's just simple subtraction here if they're on opposite sides of the arrow. 14 minus 0 will still give me 14. 6 minus -1, it's weird, it sounds weird when you say minus minus, will give me an atomic number of 7. So carbon actually becomes nitrogen. It moves up the periodic table instead of down like on the alpha particle one. Okay, and it becomes nitrogen 14, which also is radioactive and will also lose particles. Okay, here's what that process would look like. Notice my nucleus is still the same size. It still has a mass of 14, but now I've lost my little teeny tiny beta particle, which has lots of energy, so I give it a little bit bigger arrow. Mass number didn't change because I just traded 1 neutron for 1 proton. And beta particles are able to penetrate surfaces because they're smaller and they have a very small charge. They have that negative charge. So they're able to squeeze through the little gaps like in your skin and in your cells. These are actually able to penetrate into your body. So beta particles can be dangerous. Gamma particles, gamma radiation, on the other hand, are very dangerous because they're high energy. They have no mass whatsoever. It's just energy. Gamma rays are emitted during any nuclear decay. Okay, an example would be thorium breaking down into radon. It loses an alpha particle, but in the process, it still loses large amounts of energy, and that's what the gamma is. Notice there's no numbers next to the gamma because it's just energy. There's no charge, there's no mass. That's why they're so dangerous, because these can actually penetrate all the way through you. So gamma rays have no mass, have no charge, and they can only be stopped by layers of concrete and thick layers of concrete and lead. Okay. What's going to determine what kind of nuclear decay we're going to go through? It's the proton to neutron ratio. We'll talk more about that later on. A positron is the opposite of an electron. It's the same mass as an electron, but it has a positive charge. So it's a 0, but now instead of a -1, it's a +1. And we always write an E for positron. Okay, I know it seems like it should be a P, but to us, P means proton. We're thinking of this as the opposite of an electron. That's why we give it an E. Okay, a half-life, that's the amount of time it takes for half of the original amount of a radioactive atom to have decayed into its different stable atoms. Okay, radioactive dating is used to determine the age of organic material because everything, even you and I, have carbon-14 in us. Okay, we have a certain amount of it, and we can track the amount of carbon-14 over thousands to hundreds of thousands of years. And each time it loses half of that half-life, we can determine, that's how we can determine something's age and say that it's 10,000 years old. Well, nobody's around to see that it was 10,000 years old, but we know that it only has like a quarter of its carbon-14 left that it was supposed to have, so therefore we can determine its age. Fission and fusion, okay? Nuclear fission is when things when things are split apart. We fission, we split, okay? What happens is the nuclei are bombarded with neutrons. We're going to shoot a neutron at this guy. Okay, and then that nucleus is going to be split into something different. Okay, so in a chain reaction, the emitted neutrons react with other fissionable atoms. Here's what that means. Okay, notice my little neutron here. I'm going to hit the nucleus with it. Pew! Okay, when I did that, I created 2 new nuclei, but I also got 3 neutrons to my 1. Now these 3 neutrons are going to go back and do the same thing to another atom. Pew! And give me 3 more neutrons. And then those 3 are going to go do it again. So you can see why this becomes such a big reaction because you're adding on to it every time. That's why nuclear bombs are so dangerous because you keep exploding, you keep splitting these atoms, but you get more energy and more neutrons every time to go split things even further. Nuclear fission is used for nuclear energy and nuclear bombs because it produces large amounts of energy right here, okay, and then it also produces these 3 neutrons that can help produce even more energy. Fusion is the opposite. Fusion is when we put things together. The sun actually is powered by nuclear fusion. Fusion is when 2 different nuclei combine to form a nuclei with a greater mass. So fusion reactions release much more energy than fission reactions, but there's a problem with them. Okay, so you can see I take my little guys here, fuse them all together, and I get a new particle, a new atom from that. Okay, and I get my 2 little extra pieces here that can go on and be used as an energy source. Okay, the advantage of these is that they're very inexpensive. All I need is hydrogen, and I fuse it together to make helium. That's all this is. I took those little hydrogen atoms and I made a helium atom out of it. Okay, so I can get lots and lots of energy and not have to spend a lot of money. The problem with it is it's really hard to contain those high temperatures that are needed to start the reaction. To actually fuse together hydrogen atoms, it takes large amounts of temperature, like large amounts of energy, large temperatures, which is why it occurs on the sun and not here on the planet Earth. Okay? What I need you to do is go back to each of those keys, make sure you understand the keys, make sure you understand where all these answers came from. Please ask questions. Go back and look at those chemical reactions because that's what we're going to spend a lot of time with. I'm going to ask you to do reactions where I'll give you a certain unstable isotope and it's going to break down and you're going to have to give me the products, whether it's alpha, beta, etc., etc. Okay, the answer keys will be posted. I'll be here to help, but if you have questions, contact me at jkubuske@gocathedral.com or visit us at mrkubuske.wordpress.com. Have a great day.